Yeah. In real system, we live in a finite temperature, not a zero temperature. Therefore, we should take into account the finite temperature contribution and the temperature condition in quantum statistical mechanics. We should consider for Fermi-Dirac distribution. Because electrons are fermions at finite temperature, and the probability of the state and here the electron gas at finite temperature should follow the Fermi-Dirac distribution function, and the number of electrons, the occupied number of states is that Fi means that Fi is the probability of the quantum states, and all the quantum states can be like this. And also from the Fermi-Dirac distribution function is that Fermi function is that 1 over exponential epsilon I minus mu over kBt plus 1. And here mu is the chemical potential. And the chemical potential is the energy. Chemical potential is defined by that free energy derivative with number. And here, when you increase the particle number, the energy increases. It is a chemical potential. For example, for many particles may have the increase of free energy also significant. Therefore, in that case, chemical potential is very high. But in small particle system, the energy may have the variation can be think about it. And the chemical potential anyway, it is energy gradient. Energy gradient by increasing the number of particles or a decrease of number of particles, and therefore the particles evolves from the high chemical potential to the low chemical potential. Let's think about that. And there is a there is a class and in a school, and here it is class 1 has so many students here. And also because in elementary school, and the students is very active, and they are very busy, the busy room, and also it is a high chemical potential. And the other room, and just only the small students inside, and also it is low energy. And when if there is if we remove this this one, then this high chemical potential can be through into the low chemical potential side. Then finally it becomes equilibrium state. Therefore, the concept of chemical potential is the particle diffusion driving force. And anyway, it is a Fermi-Dirac distribution function, and it is a temperature dependent function in the energy eigenstate, and also different with the chemical potential. And anyway, when you study further, I assume that you already know the statistical mechanics, and you may study for Fermi-Dirac distribution function in the statistical mechanics class. And here, the energy is that h bar square over k square over 2m. Some may know the distribution function with the chemical potential is that here it is Fermi energy. and also it is energy. Then here it is we call it is chemical potential, and in other words, it is a Fermi energy. It is 1 or 0. It is in this case t equal to 0 case. T equal to 0 case, it is below the energy, below the Fermi level, and it is totally occupied. At finite temperature, in the higher energy, there is no particles, because it can be understood that at zero temperature, all the particles occupy inside the Fermi surface, and it means that inside of this energy, Fermi inside of the Fermi surface, below the Fermi energy, all the particles occupy the probability in the Fermi surface. The probability the particles exist in the Fermi surface is 1. But in the outer side, there is no particles. It is a zero temperature case. But in finite temperature, the electrons have an excitation to the more higher energy. Therefore, it becomes whole, and it is electrons. There is a hole and electron pair can create it near the Fermi level. It is a Fermi level, and in the vicinity of Fermi surface, and the hole and electron generates at finite temperature by the thermal excitation. Therefore, at finite temperature, the probability of the existing below the Fermi energy decreases, and this is This is a hole. It means that particle. It is a hole generation. It is electron generation, and also the chemical potential increases. It is electronic chemical potential. It is a whole chemical potential, and because two kinds of particles generated, therefore in the vicinity of the Fermi level, two chemical potential should be considered. It means that it is that in this side, it is the energy. This energy level is the electronic chemical potential, and this energy level is whole chemical potential. Therefore, then it is a concept of the Fermi direct distribution function. Therefore, in ground state, it means that t equal to 0, and this Fermi function equal to 1 at the if the energy below the Fermi energy, and this Fermi direct distribution function is the probability of the probability electrons, and here is 0 for energy is higher than the Fermi energy. And what is a Fermi energy? Fermi energy means that the definition of Fermi energy is a zero temperature chemical potential. Zero temperature chemical potential is the Fermi energy. Fermi energy is the zero temperature chemical potential. Yeah, okay. Here, then, because here we should think about that the energy and the number of carrier density at finite temperature. At finite temperature, the energy can be calculated in the D space. Should have the also here in K space integration, and here 1/2 pi cube 1 over 2 pi cube is the unit volume, unit cell volume of the in K space is that 2 pi over L cube is the unit cell volume. Therefore, here in the reciprocal relation and for integration with momentum space is that 1 over 2 pi cube should be included, and also here because of the 2 electrons and spin up and down we multiply 2, and also the energy should be integrate with whole the momentum space, and also here multiply F Fermi-Dirac distribution function is the probability of occupation of electrons. Therefore, it is an energy dependent Fermi-Dirac distribution function should multiply, and therefore it is that volume integration of in momentum space over 4 pi cube epsilon k dk, dk also here. Yeah, it is the energy, and the total number of concentration is a number divided by the volume, and also it is momentum space integration, and the factor, the prefactor is 4 pi cube, and the Fermi-Dirac distribution function itself is the particle number concentration. Here, as I said, the volume in momentum space is that pi kf cube, and dvk is that 4 pi k square dk. Therefore, and when we think about the integration dk over 4 pi cube and the f function, any kinds of f function, is that integral 4 pi k square pi square k square dk and f. Here we know that epsilon is that h bar square k square over 2m. Therefore, d epsilon is that h bar square k dk n over m. And also from this one, and k equal to square root 2me over h bar. Therefore, k square dk, therefore we should calculate k square dk. K square dk is that k and k dk, it is k dk is that m over h bar square d epsilon. Then k also, it is a k, therefore it is that h bar cube m square root 2me d epsilon. Therefore, it is a k square. Let's apply this value because k square dk apply to here. Star, then star becomes and h bar cube pi square m square root 2me d epsilon f epsilon. Because the energy should consider from minus infinity to the infinity, and let's define that let's define it is the G epsilon. Then here, let's define that G epsilon is that h bar cube pi square m square root 2me. Then it is that from minus infinity to the infinity d epsilon G epsilon f epsilon. What is the physical meaning of this one? The physical meaning, then because we also calculate G epsilon and D epsilon is that it is a density level. Here, for example, it is a disintegration considering for the number of states. It is number of states n over v. Therefore, it is a number n over v. N means that the number of electron levels. Therefore, the consideration is that here 1 over v and the number of electron levels in the energy between epsilon and epsilon plus d epsilon. Here we call that it is a density of state, density of level. It is a density of level per unit volume. Here, and the important thing is that this density of state in three-dimensional momentum, and it is proportional to the square root of energy, and therefore, then this density of state we call it is a density of states. Density of state also very important physical concept. You do not need to remember this exact formula, but you should remember that it is proportional to the square root epsilon and the physical meaning of the density of states. And density of states is the density of energy level with respect to the energy. In energy, with increasing the energy density, available energy eigenstate also increase. For example, when you consider for this Fermi surface, and here it is a density of state is just only 2. But in the next energy level, and this one is eigen energy degenerated because it is that the same energy level, same energy. It is h bar square k square over 2m. K square is same 1 1 1. Is k scale is same because it is a triply degenerated. Therefore, density of level in the next energy level is that 1 to 6 eigenstate. And the other one is the more higher energy also can increase more and more, then the degenerated states increases more and more. Therefore, the degenerated state means that the density of energy level. And therefore, the degenerated state increases with increasing the energy level, but it is proportional to the square root of energy. Like this. It is a density of state. Density of state of a free electron in three-dimensional space. In two-dimensional or one-dimensional system also different, and also this density of state is that m over h bar cube pi square, and also square root 2me, and it is energy is higher than 0. Otherwise, and it is 0 because there is no negative energy. And here, the density of state in free electron can be let's consider in more detail. And the Fermi energy is that h bar square kf square over 2m, and the carrier density is that from here, and also from this carrier density, and n equal to kf cube over 3 pi square, and therefore kf is that 3 pi square n to the 1/3. Therefore, the energy, this Fermi energy is that h bar square over 2m and 3 pi square n to the 2/3. Therefore, the density of state at the Fermi level, I always say that the Fermi level is very important because all the physical phenomena is observed near the Fermi level, and the Fermi level, because at zero temperature and the room temperature is close to Fermi energy, and therefore the density of state at Fermi level is very important. And here it is that when you calculate the density of state is about m over h bar cube pi square and square root 2m epsilon Fermi energy. Because 2m epsilon f is h bar square kf square, and therefore it is h bar cube pi square m, and it is h bar kf. Therefore it is h bar square pi square m kf. Then, and from here, and the kf and kf can be calculated. Let's consider for n over epsilon f. Then n is that kf cube over 3 pi square, and also epsilon f is that 2m over h bar square kf square. Then it is that 3 pi square h bar square 2m kf. Therefore, mkf over h bar square pi square is that 3 half n over epsilon f. Therefore, when you substitute this one in here, and we can conclude that the density of state at the Fermi level is that mkf over h bar square pi square equal to 3 half n over epsilon f. Yeah, okay. And we conclude, we say that the Fermi density of state Fermi level physically important. You do not memorize this equation, but the physical understanding is very important. It is a density of state at the Fermi level. Then from this one, if the carrier concentration increase, the density of state increase. Also, Fermi energy decrease, the density of state also increase. Yeah, here, we should take into account from the density of state near the Fermi level. Then we can calculate the specific heat, electronic specific heat from the Sommerfeld theory.